Well, y'all, this is Darrell Lee Berry Jr. Make sure you like, subscribe, share, all those good things. I have my Patreon there. You can sign up for tutoring, individual or group, through PayPal or Patreon. We're still working on my review for my exam on tomorrow in linear algebra. I'm progressing through chapter 2 right now. So we're on example 5 in section 2.2. Then I'll move to section 3.2 and then 1.5. So let's start with example 3, continuing where we left off. So example 3 says, continuing from example 2D, and this, by the way, is proof of identity matrix. If L is a line in R2 through the origin, the reflection across L is the map RL R2 that sends X2 as mirror image in L. Okay, we begin by writing. So let's take a look at the diagram is starting here. So we have drawing my axes first. And then we have L going through the origin. And we have X, which will be here. So we're going to project across L. That makes me wonder if I thought about one of the homework problems incorrectly and did a projection onto L rather than across L. So I have to see. Reflection across L. So X equals X parallel plus X perpendicular. And that's perpendicular and parallel to L. This is X parallel, and this is approximately X perpendicular. So it'll be only as tall as X on the perpendicular. Therefore, the reflection about L of X equals X parallel minus X perpendicular. I see. So what they're doing is they're saying this is the reflection down here. It's a little bit past the midpoint. So this is the reflection about L of X. So what it's saying is this line here I may have drawn it a bit too far, but it's not a big deal. But this line here is X perpendicular. These are X parallel minus X perpendicular. That's what this line is. X perpendicular okay, X perpendicular equals X minus X parallel. So that equals X minus X minus X parallel. So that equals 2X parallel minus X. All right, clear enough? If anybody has any questions, if anybody turns up, you could ask live if you turn up while I'm still live, or ask in the comments. Using the notation of example 1C, we have X parallel equals the projection of L onto X. Remember that before? X parallel equals the projection of X onto L, that is. So reflection about L of X equals, oh, 2 projection of L onto X minus X. Or in functional notation, equals so the 2PL minus I. Not sure about that one. We must do an inverse somewhere. That's the only thing that can make the identity. Let's check the identity matrix again, so to make sure I'm clear on what that is. A times C is the identity matrix. believe I remember seeing it. So we can find. You know, we're solving for the identity matrix. We have to have the matrix here, and then have the identity matrix there, and solve the matrix to get to identity matrix, and then we have the inverse. So it must be RL X X inverse equals 2 PL X X inverse minus X X inverse. And then it gives us RL equals 2 PL minus I. Because the reflection is going to whatever times the identity matrix gives whatever that is. And just the identity matrix by itself is just the identity matrix. So I'll go with this for now. But if my memory is serving me correctly on that. All right, so this is where we are here. Where I is R2 to R2 identity map. Gives you the same thing. One can now use the result of exercise 11 to deduce that RL is a linear map. It's worth noting that RL of X is the vector on the other side of L from X that has the same length as X and makes the same angle with L as X does. So what it's saying is you have L, you have X. This is RL of X. In particular, the right angle with leg front is parallel and hypotenuse X is congruent to the right triangle with leg X parallel. How do you remember what congruent means? Same direction? The right triangle with leg parallel and hypotenuse X. It's congruent to the right triangle with the leg. Same leg. Hypotenuse reflection of x. Okay. So that's how we know it's a reflection, because of these two triangles. They're the same triangle but flipped. This is an example of the technical wording. The hypotenuse axis for one and R axis is the other one. Right, example 4. We conclude this discussion with a few examples of linear transformations from R3 to R3. So these are linear transformations, R3 to R3. So for A, let A equal -1, 0, 0, 0, 1, 0, 0, 0, 1. Because mu A leaves the x2, x3 plane fixed, right? X2, x3 are fixed, so they're just the identity matrix. And x1 is sent to negative x1. Thus, AX equals reflection. Oh, reflection about the x2, x3 plane. Because x2, x3 is the same, but is on the opposite side. Okay, I can see that. And it says mu A equals, is the function, B, mu B equals B equals 0, -1, 0, 1, 0, 0, 0, 0, 1, right? So what do we have? We have x1 goes to x2. We have x2 goes to -x1. And we have x3 fixed. That's what I'm seeing here. And we'll take a look and see what the book says. So if I was to look at this, I would say that it was a 90 degree. I have to see. Then we have v x equals b x1, x2, x3. So that equals 0, -1, 0, 1, 0, 0, 0, 0, 1 going across the rows. So that equals -x2 x1 and x3. So x3 is fixed. So actually x2 into negative x2. So this column, the column in the matrix goes to the first point in the vector. So it goes like this. So x1 goes to x2. x2 becomes negative x1. x3 is fixed. I guess I don't think I'm describing these two properly. Let's see how the book describes it. We see that UB leaves the x3 axis fixed and rotates the x1, x2 plane through an angle of 90 degrees. So the flopping of the signs of one of them and swapping the places of x2 and x1 is a 90-degree rotation. Thus, xb rotates an arbitrary vector x in R3 an angle of 90 degrees about the x3 axis. Let's picture, because x3 stays the same whatever x3 is. All right. C, and we'll call this the 90-degree rotation. So for C, we have A equals 1, 1, 1, and X is in R3. We know that the projection of, so A is 1, 1, 1, X is in R3. The projection of X onto A is given by the projection onto A of X equals X dot A over magnitude of A squared A. So that equals A is 1, 1, 1. So I can see how that's a square root of 3 squared. X dot A is going to be A1 plus A2 plus A3. Is going to be X1 plus X2 plus X3 times the vector A, which is 1, 1, 1. That's going to be 1/3 X1 plus X2 plus X3, X1 plus X2 plus X3, X1 plus X2 plus X3. Projection of X onto A. Projection of X onto A. So this matrix must be, hold up. We'll see. Thus, if we define the matrix C equals 1/3, 1, 1, 1, 1, 1, 1, 1, 1, 1, we have the projection of X onto A equals C X. Now, I'm not sure why that becomes all ones. Because wouldn't that have X in each one of those values? And there would be the dot product. Let's test it. So we have C X equals 1/3, 1, 1, 1, 1, 1, 1, 1, 1, 1, X1, X2, X3 equals 1/3, X1, X2, X3, X1, X2, X3, X1, X2, X3. And we know that this is a 3 by 3 and a 3 by 1. So this needs to be a plus. This needs to be a 3 by 1. All right. So it looks like it does work out. Projection of X. Therefore, the projection onto A of X equals CX. So basically, what we did was we take 1/3 X1, X2, X3 plus all the way down X1 plus X2 plus X3, X1 plus X2 plus X3. All right. So that equals 1 over 1/3, 1, 2, 3, 1, 2, 3, 1, 2, 3, and X. And then we're just going to call that whole thing C. All right. So we know that is the projection onto A of X. So if the X is big on one side, it stays big on the other side. Right? The standard matrix of a linear transformation. So why don't we take a break here, and I'll be back starting with the standard matrix of a linear transformation. Like, subscribe. I'll see you later. Back in just a little bit, at the most 20 minutes.